So let me start today with the second module, that is crude oil characterization. And I would request all of you to pay 500% attention to what I'm going to talk about today, because this actually forms the foundation of petroleum refining engineering. Um, Everything that we will discuss when we talk about various process units, the various properties, the various concepts, would actually rely very heavily on what we are going to discuss today. So please remember this, and there would be actually questions and quizzes, which actually would be very strongly, try to check whether you have actually learned this or not. And in fact, as I go through, if anybody is not able to understand something, please interrupt me, and I'll go through it once more. And I will go slowly. So please pay full attention. It might appear to be very easy and simple, but it's very important for you to understand this. So what you will learn in this module is how we in the oil industry characterize crude oils, and what do we mean by something called as crude assay, and how do we determine all these impurities, and how do we classify them in terms of sediment, salt, sulfur, etc., etc. Why this is important? Okay, why this is important is because actually crude oil is very complex mixture. It's a very complex mixture. There has not been a single individual or an organization or a laboratory or even an analytical technique which is invented so far, which can identify each and every molecule in a petroleum, in a crude oil. People have actually, what I should say, fantasized that crude oil would have something like 1,000 components or 2,000 components and stuff like that. But believe me, I've been in this industry for 46 years now, and I have never seen a full component-wise analysis of crude oil. Okay? So what do we do? Since we don't have a capability to analyze crude oil in its complete detail, we need to actually develop methodologies and procedures to understand and characterize and classify, and more importantly, classify crude oils. So that if somebody talks about a particular crude oil, we know exactly what kind of crude oil it is, and whether we'll be able to process that crude oil in our refinery. So as you go along, see what you see on this graph actually is on the y-axis is the percentage, on the x-axis is the boiling temperature in degrees Celsius. So as you dig deep into the barrel of the crude oil, you will find that generally the normal and the isoparaffins concentration, it goes down, and the naphthenes actually are very high to begin with, then they also go down. These are like single ring naphthenes, basically cyclopentane and cyclohexane, or their alkylated derivatives. And then actually the condensed naphthenes, the two ring and the three ring and the four ring naphthenes, they start appearing around this temperature. The alkyl benzenes, they continue right across till the heavy ends. But then, as we go along, you get polynuclear aromatics as well. So ultimately, when you go towards something called short residue, which doesn't boil even at 550 degrees Celsius, I mean, so we boil it, of course, under vacuum. Because if you remember, I told you last time that any hydrocarbon, and I repeat, any hydrocarbon, if you heat it up at about 360, 365 degrees Celsius, it cracks. It doesn't boil anymore. So if you want to boil it, you have to actually boil it under vacuum so that the temperature is low. And so if you are looking at the heaviest end of the barrel of the crude oil, obviously it essentially doesn't contain any amount of normal paraffins, very little single ring naphthenes, but appreciable quantity of condensed naphthenes, some amount of alkyl benzenes, but appreciably polynuclear aromatics. So if you look at asphaltenes, this is the kind of material that you're looking at. The same thing is more easily seen from a chemistry point of view in this graph where I have plotted carbon number on the y-axis versus boiling point. It is roughly, matching with that table that I showed you earlier of various hydrocarbons. Fractions that you actually distill from crude oil. So here they are shown like naphtha, and then kerosene range hydrocarbons, which we call as middle distillates, which include kerosene or jet fuel and diesel as well. And you're going right up to something like 365 degrees Celsius here. On the top is degrees Fahrenheit, the bottom numbers are in degrees Celsius. And then you actually get into the vacuum distillation column where you actually distill these hydrocarbons under vacuum. So we call it as a light vacuum gas oil and the heavy vacuum gas oil. So these are changing in terms of the boiling point, and then of course something which cannot even boil at under high vacuum. We are talking about vacuum of the order of absolute pressure of 10 millimeter mercury. And so that is about 545 degrees, 50 degrees centigrade. So if you look at the various hydrocarbons which are present, you look at naphtha, you have basically paraffins. This is actually the normal paraffin graph that you see here. This is hexane, then decane, then C14 paraffin, etc., etc. And then you actually go through the aromatics, and this is actually the graph for naphthenes. So single ring naphthenes and then multiple ring naphthenes as you go through. So if you look at light vacuum gas oil, etc., or even diesel, you start even in kerosene and diesel you start getting two ring naphthenes. And then if you look at aromatics, this is the graph for aromatics. You do have alkyl benzenes like benzene, toluene, xylene present in the naphtha. But the moment you enter the jet fuel, you start getting, two-ring aromatics and maybe naphtheno aromatics, etc. And then ultimately complex molecules going up to porphyrin here. And then you have these polar compounds which are actually having nitrogen or sulfur, etc. So this is how they distribute. But there is no way at all to actually identify in terms of percentage each and every molecule. So we have to understand, and we have to actually evolve a method of how you classify, given the fact that you cannot actually determine these hydrocarbons analytically. So how do we actually represent the crude oil? So we come to this whole discussion of crude oil classification. Overall, what happens is that there are four ways by which we understand crude oil in our industry. Essentially, most important is where does it come from? Okay. So if suppose somebody tells me that this is a crude from Saudi Arabia, I know the typical value, the typical data on such crudes. So I have a very good idea in terms of so the refiner, if it is coming from Dubai or whatever. Now there are two crudes which are used as a benchmark today. One is called the Brent crude. So please remember this Brent crude, and the other is called the WTI, that is West Texas Intermediate. The Texas Intermediate is actually used as a standard or a benchmark in the US, while Brent is used as a standard or a benchmark in Europe. So Western Texas Intermediate is actually a kind of a intermediate crude between I'll talk to you about what is an intermediate crude. But Brent actually is what is actually dug out from the North Sea. That is deep sea mining just north of Norway. It is actually somewhere between UK and Norway. So that is the entire ocean area, which is called North Sea. And of course, you have Middle East, where you have various countries like Kuwait, Basra light. Basra is from Iraq, and then Iranian crudes, and so on and so forth. So location is very important. Crudes are classified in terms of their location. And then the relative weight or viscosity. So we have these terms whether it is light crude or heavy crude, and that is where actually the definition of intermediate comes in. So intermediate is neither a light crude or a heavy crude, and we will in the next couple of slides I will tell you uh, the quantitative definition of light or heavy crude. Right now we are just talking about it qualitatively. So basically, it's a relative term. Light can be lighter as compared to something else, or heavy can be heavier as compared to something else. So basically, right now it is just pure qualitative, but the next very slide I will actually define it in terms of actual value. So the number of carbon atoms, of course, depend upon, and so the more actually the crude oil contains these heavy components like asphalt, etc., the heavy it becomes. So it's either light, intermediate, or heavy. So this is also like, for example, in Saudi Arabia, we have light Arabian crude and the heavy Arabian crude. And there is an extra light Arabian crude. So extra light means it's much lighter. The density is much lower. And the third criteria is what type of hydrocarbons are predominantly present in that crude. Whether the crude is paraffinic in nature, whether it is mixed or it is naphthenic. So basically, every crude will have aromatics, and some crudes have high aromatics. Like last time I mentioned that the crude that we have in India, like the Bombay High crude or the Assam crude, both crudes are highly paraffinic in nature, but also have higher aromatics. In other words, if you look at the four hydrocarbons that we talked about, the paraffins, isoparaffins, naphthalene, and aromatics, the crudes that we have in our country, like Bombay High or Assam crude, do not have much of naphthalene, so they have paraffins and aromatics. The fourth is, of course, the sulfur. One of the, as I told you, I think by this time you must be pretty aware of the fact that sulfur is the one of the most important, impurities present in crude oil. And so basically, what is the sulfur level of that crude? So if the sulfur level is low, we call it as a sweet crude, and if the sulfur level is high, we call it as a sour crude. Somehow these terms have got stuck in the industry, and this is how. So the crude oil could be, let's say, from Dubai. So it could be a Dubai, Dubai blend. It could be naphthenic crude, intermediate crude, and sour. So, and you can have various combinations of this. So basically the source, whether it is light or heavy, what kind of hydrocarbons are predominantly present, and whether it is low sulfur level. Now coming to the actual definition of the crude in terms of light or heaviness, obviously I think it's very common. It's common sense to actually link it up with the density of the crude. So the density of the crude is used for weight to volume or vice versa calculation. So density is very important, and generally it is at 60 degrees Fahrenheit or 15.5 degrees centigrade. You will find that this industry is extremely dominated by the FPS units, by the American units, because a large amount of development and even now a large amount of technology development, know-how, science actually originated, and the US actually leads in this particular industry. And you will see that there are other terminologies which are used, which we use, which is actually originated from the US. Density is also used to check the consistency of the crude supply. So basically, if suppose you are getting crude from the same source, let's say from Saudi Arabia, and it is termed as light Arabian crude, then actually and so from that, when you measure the density of that crude oil, that itself will tell you whether it is the same crude oil that we received last time or is there any variation. It is also a very important property used in a very large number of correlations, and we'll talk about that in greater detail in the next class. But basically, as you know, density is just mass upon volume, and there is a term which has been defined by the U.S. industry called API gravity. API stands for American Petroleum Institute. API gravity, which is 141.5 upon specific gravity at 60 degrees Fahrenheit or 15.5 degrees Celsius minus 131.5. So for water, where specific gravity is 1, API gravity for water is 10. 141.5 minus 131.5. And this API gravity is an indication of how light or heavy crude it is. So when you actually, when the crude oil producer supplies crude oil, he actually mentions whether what is the API gravity of this crude. And generally, so this is how we classify the crude oils in terms of API gravity. If the API gravity is greater than 30, we call it as a light crude. So in other words, if the specific gravity is low, then 141.5 upon density, because since density is in the denominator, API is high. So higher API crudes means lighter crudes, and low API crudes means heavy crudes. Please remember this. And the API is a major factor for crude pricing. In fact, even 2 years in this industry, actually you become very converse. You know, you actually the only way you can understand a crude oil is basically by somebody telling you what is API gravity. It is called degree API. So people actually like the way you write degree Celsius with a small zero at the top, same way you write degree API also. And so the intermediate crudes, which I mentioned about the WTI, if you remember, this WTI, so that API would be somewhere between 20 and 30. So this is a very important classification by which we try to understand crudes. And believe me, although it might look innocuous, it might look very simple, and to some extent, to some of you, it might look even stupid. But API gravity is something which actually is extremely important for us to know of any particular crude oil. And if you look at the sulfur part, whether it is sweet or sour, again, sweet or sour depends upon whether the crude is light or medium or heavy. So for crudes which are in the range of 35 to 60 API, depending upon whether the crude is sweet or sour, the sulfur levels could vary between 0 to zero point 0.5 or greater than zero point 0.5. So you can see when it's one thing very clearly here is that even the definition of a sweet or a sour crude really depends upon whether the crude is light or heavy. On the other end, if you look at the heavy crude, the heavy sweet and sour crude, the API is low, but the level of sulfur levels go up because actually heavier crudes by definition have a higher sulfur content. You might actually find some heavier crudes have low sulfur, but and you know one of our greatest examples is from our own country. That is uh, the 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 crude oil from Rajasthan, which is a new discovery, relatively new discovery. We only discovered this about 20, 25 years ago, this particular oil field. It is in Barmer, and we have a completely new refinery which was set up there from Hindustan, which is a JV between HPCL and Mittal Group called HMEL, Hindustan Mittal Energy Limited. And they set up that refinery in order to process the crude that is actually produced there in Rajasthan. And that crude is heavy crude, but it is sweet crude. It has low sulfur. So those are the exceptions, but generally the heavier crude have higher sulfur. So here again, if it is less than 1% sulfur, it is called as a sweet crude, but it is heavy sweet, and greater than 1%. So the same definition of sour and sweet can vary depending upon whether the crude is light or heavy. For medium crudes, of course, it is somewhere between zero point 0.5 and 1. So this is how actually you classify crudes. One is, of course, in terms of the location where it is coming from. Second, of course, gravity, and third, whether it is sweet or sour. And this is actually give you some idea about the various crudes. In fact, what I have tried to do is that I have tried to include as many crudes as possible from our own country. Like Narimamam crude is actually from down south, below, even south to Pondicherry, in a place called Kothalam. And this is an intermediate crude, which has got pretty high API. It's pretty light crude actually. Then Ankleshwar crude, which is actually South Gujarat, again API high. Then this I actually is not in terms of gravity, but actually in terms of the hydrocarbon type. So this is P, means which actually is a paraffinic crude. So we actually classify, there's another classification of crude which I'll talk about. So let me actually do that before I come back to this slide. See, the other types of classification of crudes is basically in terms of the type of hydrocarbons which are presented dominantly. So the crude could be either paraffinic, or it could be naphthenic, or it could be a mixed between the two. And so generally we want to know like what kind of hydrocarbons are dominantly present. The reason is that depending upon like for example, just because Assam crude has high wax content, so we thought about putting up that wax plant in Numaligarh refinery, and there was a wax plant already operating in Digboi. The same unit you cannot put up when you're processing a Middle East crude, let's say coming from either Saudi Arabia or Kuwait or Dubai or Oman, etc. Because those crudes do not have too much of wax. Those are basically naphthenic crudes. And those crudes are useful to make base oils, to make lubricating oils. Because there are two things you don't want in lubricating oils. We don't want paraffins there because it actually increases the freezing point, and we don't want aromatics because it actually reduces the viscosity index. And the viscosity index is something you need to find out and define and let me know. The type of hydrocarbons is very important. Like Bombay High crude. Bombay High crude is mostly paraffinic and it has aromatics. It has got no naphthene. So this is very important. In fact, you could even have situations where actually you could have a molecule like this, and this is not something which is uncommon. I didn't make it up for you. It is actually something which is present in crude oil. You just see this. You have a benzene ring, along with that a naphthene ring, and then a long alkyl chain, something like a 13 carbon number alkyl chain. And what do we say? This particular molecule, is it aromatic, is it naphthenic, or is it paraffinic? From atomic point of view, an atom common to two structures or aromat will be considered first. So actually, if you ask me, the way we look at this molecule in the industry is that we'll first classify this as an aromatic because there is an aromatic ring to begin with. So the first moiety is actually the aromatic ring, and then you have the naphthene and the paraffin. So depending upon actually what use you use it for example, suppose if this molecule is in lube oil, it will be actually a most welcome molecule because it is less aromatic and more non-aromatic. So these things actually you may not have heard in organic chemistry earlier, where actually you talk about aromaticity, paraphinicity, or naphthenicity in a relative term. But when you but lube oil, in crude oil has almost all kinds of hydrocarbons. So some of these hydrocarbons, like the one that you see here, it is less aromatic and more paraffinic, and so and so forth. So actually, depending upon what application you want to use it for example, if I want to use this, if this molecule is present in lube oil, I will not remove it because it is, although it is aromatic, but it is less aromatic. So knowing all this, actually, now we come back to our various crude oils. So I stands for somewhere between paraffin and naphthene. And if you look at Bombay High, again, we call it as intermediate because, of course, there's a balance between the paraffins and the aromatics here. But you can see the API gravity is still low. Hira is again a well in the Bombay High area. Kalol, Ratna, etc. So Basra is actually an imported crude from Iraq. And this is again 30 North Gujarat, and then Narkotia, and then Kuwait. You can see actually as it goes down and down. See, as the API gravity keeps going, still you reach Santhal. So, so again, see what I would like you to remember. I'm 100. You cannot remember these codes, and I don't want you to mug up or try to memorize this data. But what I was trying to tell you is that crude oil, the way it is classified, is very easily seen in this table. So you have crude, so you need to know where it is coming from. So that's why the name is written here. Then the density of the API, that is very important. So from this API, I know whether it is light, heavy, or somewhere in between. And the type, whether it is naphthenic, whether it is paraffinic, or somewhere in between. And sometimes we also actually try to give this data as well. That is, suppose if I distill this crude at atmospheric pressure, how much quantity will distill up to 370. Now, this data is very important. I'll tell you why. Now, this crude says that, Narimomum crude says that up to 370, 80% of that will get distilled. Now, this crude is quite precious because I can make a large quantity of naphtha, kerosene, and diesel from here. But if you look at something like this crude, for example, only 22% up to 370. It means this crude is not, I'll have to do something else. I'll have to actually take this material and do some cracking or do something, while otherwise only 22% has been distilled off. So the naphtha, kerosene, and diesel, what we call as light fractions, they're not available in very large quantities. Roughly, if you want me to tell you about a typical ballpark number, if you're distilling, let's say, a Middle East crude, you're looking at something like 60% or 55% of the crude distilling off at the atmospheric pressure at about 370 degrees centigrade, about 60-65%. So it really varies from 55 to 65. That is the typical most desirable range that we look at from the industry perspective. Anything lower, it is heavy. Anything higher, that means it's a light crude. And of course, a vacuum distillation. See, for example, let me tell you. See, this is a good time to tell you this. If you look at Assam crude, almost 65%, 65% of the crude distills off at 370. So many refineries, when they came up in Assam, the Digboi refinery, the Guwahati refinery, uh, they did not have a vacuum distillation column. They just have atmospheric distillation column. And even today, they continue to have atmospheric distillation column. Of course, over a period of time, the Digboi refinery has got modified, and now they put a vacuum tower. But actually, Guwahati still doesn't have a vacuum tower. Okay, so because they didn't see the need to put a vacuum tower, so whatever was coming out from the bottom of the atmospheric column, that they actually put it into a process called delayed coking and made pet coke out of it. So so all this data is very important in terms for you to define or design a refinery configuration. The like the way we defined light or heavy crude in terms of numerical values. That means we gave a quantitative definition of a crude, whether when do we call it as light, when do we call it as heavy. Similarly, when you talk about paraffins, naphthenes, aromatics, or intermediate type of crudes, those are also relative terms. Like actually, this example showed you, it's all relative. So we need to actually come up with a quantitative definition of the crude oil in terms of paraphenicity, naphthanicity, or aromaticity. And one way, one so this UOP, when we call it as a UOPK or a Watson K, K is just a letter K in the English alphabet. That is defined as cube root of the boiling point in degrees Rankine upon specific gravity. So this is, whatever. So suppose if the fraction has a boiling point of, let's say, 100 degrees Celsius. So 100 degrees Celsius means 212 degrees Fahrenheit, and 212 plus 460, that is the degree Rankine. Now, don't ask me as to why we are looking at degree Rankine and not degree Kelvin and so on and so forth. As I told you, this whole science got developed in the US, and they use their own units. And because of that, actually, the industry is stuck using these units. So even today, the UOPK or the Watson K is calculated by this formula. That is cube root of boiling point in degrees Rankine. So if suppose you know the temperature in degree Kelvin, then you just have to multiply by 1.8, as you know, to convert that to degree Rankine. And and that upon density. Now, this UOPK, if it is greater than 12, the crude oil is predominantly paraffinic. And if it is less than 11, it is naphthenic. So you can see that the window is pretty narrow. Okay, the window, and this actually is not only for crude oil. Okay, this particular parameter holds true even for various fractions. So if you're talking about gasoline fraction, kerosene fraction, diesel fraction, there also UOPK is applicable. And if suppose I have a diesel fraction whose UOPK is higher, that means I know that this diesel has more paraffins, and that means it would have a higher melting point. That means it will have a higher cloud point. That means I'll have to actually do something to isomerize those normal paraffins to isoparaffins, and thereby actually reduce the pour point or the cloud point and so on and so forth. So that's it. That is how we actually infer what we need to do for either crude oil or the petroleum fractions derived from crude oil. So UOPK, or it's also called as a Watson K, they mean one and the same. It is actually given by cube root of temperature, boiling temperature in degree, and which temperature to use. In fact, what is the definition of the average boiling point, that we will discuss. I mean, I will let you know. Like if suppose there is a petroleum fraction boiling from in the range of 100 to 200 degrees Celsius. So do we take 150, that is 200 plus 100 upon 2, or do we take something else? So that is something that I will define to you. Like what do we mean when we say average boiling point? Okay. So just for now, just remember that you have to use an average boiling point in degree Rankine, cube root of that upon density, and that decides the paraphenicity or naphthanicity of that crude oil. There's another parameter called BMCI. It is called the Bureau of Mines Correlation Index, and it is given by this formula, which is 48640 divided by average boiling point in degrees Kelvin. Mercifully, this is in degrees Kelvin because this particular index came much later. And this particular parameter is more used for feedstocks, which are used to make carbon black. And carbon black is used in making a tire in the tire industry. As you know, all our tires are black. And that blackness in the tire is because of the carbon black which is added during the massification process of rubber. Rubber by itself is white in color. Okay, whether it is natural rubber or synthetic rubber, it is white in color. So we don't we actually add carbon black, and it's appreciable quantities of carbon black which is added in the rubber, and that actually makes the rubber black. And this carbon black again also comes from the refining industry, where actually you bring it. You use a certain petroleum fraction from which, and the quality of that petroleum fraction should have good amount of aromatics in it to make good amount of carbon black, and that is why BMCI is a parameter which is used to understand the quality of the feed for a carbon black as a carbon black feedstock. It's called CBFS, carbon black feedstock. So actually, if you look at how do you understand crude, it is understood by something like crude assay. Like for example, each of us individuals, we do have what we call as birth chart or Janam Patri, and you need three data points to define, to develop a complete birth chart. Your place of birth, the time, date of birth, and the time of birth. And so basically, these three variables more or less defines the position of stars or whatever. And it tells you many more data depending upon how good the person interprets that. So similarly, in crude oil, there are three basic properties which we definitely would like to know, and that is first is API, of course, and the second is the UOPK. And then beyond that, we like to know the distillation characteristics of that, and I'll get to that in a moment. So, how does it distill? In what range does it distill? So these three, Watson K or API, sorry, UPK, API, and distillation characteristics, the three most important parameters to define a crude. In addition to that, there are many other that actually we would like to know about the crude oil. Like for example, how much is the light ends which are present, like C1, C2, C3, C4, C5, because they actually tells us the LPG potential of that particular crude, like how much LPG can be produced. The pour point, the temperature at which you can pour this liquid, the viscosity, the wax content, the asphaltenes, and the carbon residue, ash content, the water content. So these are the impurities that I have listed on the right side. And we like to know like whether it has water and how much salt it has. What is the BSNW? I have already defined these terms last time. This is like basic sediment and water, and of course the various elements like sulfur, nitrogen, oxygen, as well as metals. So this is the impurity level we would like to know as far as the main crude is concerned. These are the properties like wax content, carbon residue, asphaltene content, and the three most important properties: the density, that is API, the Watson K, and the distillation characteristic. All this data put together is actually what is called as a crude assay. And this is so when a refinery actually buys crude and the cargo arrives, along with the cargo is the documentation which actually carries the full details about the type of crude, that is what you call as a crude assay. And this is actually a quality parameter by which crude is traded worldwide. So if I'm buying a crude, I'll define what kind of crude I want to buy. And that crude, when it comes, it will come with this quality, what you call document. And this quality document of the crude is called crude assay. And we'll actually go through each one of them in greater detail. And I've already defined what is a density API and UOPK. We'll get into the other ones, like for example, the next one is the RVP, the reed vapor pressure. It is reed vapor pressure is something similar to vapor pressure. So you know that Antoine equation is used to calculate the vapor pressure as a function of temperature. So similarly, so anything which boils will boil only and only if its vapor pressure is equal to atmospheric pressure. So when water boils at 100 degrees Celsius, that means the vapor pressure of water is 760 millimeter mercury. If you actually boil the same water in a place like Dehradun, which is 2000 feet above sea level, it will boil at 91 degrees Celsius because At 2000 ppm, at 2000 feet, the atmospheric pressure is 711 millimeter mercury, and so the vapor pressure of water becomes 711 at 91 or 92 degrees Celsius. So similarly here also, but there we are actually dealing with pure components like benzene boiling point is 80.1 degrees Celsius. So benzene when it boils at 80.1 means the vapor pressure of benzene is 760 millimeter at 80.1. I think you remember all this. So here, of course, you're not dealing with the pure components, you're dealing with a complex mixture. So here actually there's a certain instrument which is used and the way that instrument was designed and the way it actually determines vapor pressure was of course a person by name Reed, and that's why actually it is called Reed vapor pressure. It is just vapor pressure, just the name got attached to that, and that actually defines it defines what is the content of gaseous and lighter hydrocarbons. So if suppose the vapor pressure is high, that means we know that so for example benzene, if it boils at so if you heat it up to 100 degree, its vapor pressure goes up, right? So I mean the boiling point of benzene at 100 degree. If you want to boil benzene at 100 degree, you'll have to increase the pressure. That means vapor pressure is higher. So lighter components have higher vapor pressure, and that what you see. The propane is 14.1, butane is 6.6, and crude oil is very low. Okay, so depend. So if you're able to measure the RVP of crude oil, you know roughly what are the light components which are present in this crude oil. And but there's a method by which actually you distill off the light ends. You strip off the crude from the you strip off the light ends from the crude, and then you carry out the analysis of that light ends by GC, gas liquid chromatography, to determine the percentage of these hydrocarbons. Why it is important? Because when we start designing the crude unit, we need to know the vapor traffic which will come up to the top, as well as actually how much LPG potential we have, so that we can design the downstream distillation columns accordingly. And this is the typical light ends. We call it as a light end analysis. Means the light end part of the crude. And here you can see that C1 non-detectable. That means there is no methane here. Even ethane is in traces, but C3, that is propane, is in the form of 0.1%. Iso C4, that is isobutane, is 0.1%. Normal butane 0.3%. Isopentane 0.3, and normal pentane 0.5. Overall about 1.3. So these are the typical numbers like 1.3 to roughly about 2%, 3%. Our crudes like Bombay High, they have significant quantity of light ends. So Bombay High, our crude like Bombay High is blessed with more LPG potential. And our country actually, as compared to any other country in the world, is a major user of LPG, not only for domestic cooking, but actually now the government has banned it. But actually, LPG was also used for transportation purposes earlier. So, and if you talk about all these restaurants or dhabas, etc., they all use LPG for cooking. Of course, it is being slowly replaced by natural gas. So we have piped natural gas. Gases. In fact, my house here has piped natural gas. We don't use LPG anymore. But nonetheless, almost and of course, because of this piped natural gas, now LPG is penetrating into the rural sector as well. So in the rural sector also, instead of using cow dung and firewood, people are the villagers are now using LPG. So LPG is a very important commodity. India still imports LPG, by the way, and this is only one petroleum product that we still import. And it is very important to know what is the LPG potential of crude oil, and that is defined in terms of light end analysis. So you have like propane, butane, and various isomers of that, and that is indicated by RVP. So if you go back to this crude assay table, we have already defined API, and now I have told you about read vapor pressure and light end analysis. What comes is the distillation curve or the distillation data of the crude oil. And I think I will discuss this and I'll stop because there's too much of this information that you need to digest. So, for a crude oil or any petroleum fraction derived from crude oil, whose composition we don't even know, the boiling point is typically represented by a curve. And the curve actually, has percentage volume on the y-axis and temperature on the x-axis. So it tells you like, from what temperature to what temperature is this material boiling. And there are several laboratory equipments which have been designed to generate this data, not only for crude oil but also for petroleum fractions. So this is, but one thing that is not specific to crude oil. It is specific. It is right across the refining industry for various process units for everything. We like to know what is the boiling range. That is the boiling curve. So this is actually what is called as a distillation curve that you see. Basically, it is a boiling curve, and there are five such definitions or the methodologies by which we determine distillation curve. One is called the true boiling point, and I'll talk about what is true boiling point. In other words, TBP. Then the second is ASTM D86. In fact, by the time we end this course, this will become part of your language, English language, D86. ASTM stands for American Society of Testing Materials. So this is a big standardization body like our Bureau of Indian Standards that we have in India. If you ever take any product, which is actually any product, whether it's an electrical product or even the water bottle from which you drink water, you would have an ISI stamp on it. ISI stands for Indian Standards Institute, and the Bureau of Indian Standards actually provides that particular standardization. So we also try to follow as much as possible standardization literature from ASTM. ASTM again stands for American Society of Testing Materials, and they have a large number of all thousands and thousands of testing methods that they have developed, which has actually standardized the way you actually characterize something. And so even density, they have an ASTM method. How do you determine density so that people, if they follow that method, they'll arrive at the same number. Similarly, ASTM D stands for actually the section number in the ASTM. And the 86 is the numerical. So the ASTM D86 is a distillation curve. Then you have this is at atmospheric pressure under vacuum. If you want to do it, it is actually ASTM D1160. So, in fact, this has become so common in our industry that we just don't even say distillation curve. We just say, do you have D86 of this fraction? So when I ask somebody, you there a D86 Behina, so he understands what exactly I mean by D86. Okay. So this is how we actually, it has become part of the language that we use in our industry when we actually communicate with each other. So TBP, ASTM D86, ASTM D1160, and then actually after the invention of gas chromatography, people have started to use GC also to determine the boiling curve or the distillation curve, and that is actually standardized by this method called ASTM D2887. And there's another one which is equivalent flash vaporization. It has more thermodynamic significance, EFV, but we don't actually use it at all because it's very difficult to actually to determine this EFE experimentally. Now, just to give you an idea, this is actually real data. This is light FCC gasoline. FCC stands for fluidized catalytic cracking. It's a process unit. in a refinery, which we will discuss and learn in great depths in this course itself. It's a very important process unit in a refinery. In fact, if you ask me, the major revenue of a refinery actually is produced from a fluidized catalytic cracking unit. And why I'm showing you this information is basically you can see, like even for a fraction, there is an ASTM D86 data. So this is how actually D86 is reported. So you can see percentage volume versus temperature. So IBP stands for initial boiling point. So when you start boiling, the first vapor that gets formed is at 44.7 degrees Celsius, and then 5% of it gets distilled by 67.9. I'll show you the apparatus in a moment. And so just remember this one, that this is how ASTM D86 or TBP or ASTM D1160 or even D2887, any of these, whether it is TBP, ASTM D86, DSTM D1160 or D2887 or even EFP, the way it is reported is shown in this table. 5% vaporized, 10% vaporized, 30% of the. So if I take 100 ml of the material and then start distilling it, so the very first vapor that gets formed, so the first very droplet that I condense is at 44.7, and then the 5% of the 100. So if I collect 5 ml to the top by at 67.9, I would have collected 5 ml. By 68.4, I would have collected 10 ml. By 68.9, about 30 ml, and so on and so forth. And ultimately, 95% of it boils out by say 76.1, and the final boiling point is 90. This is a pretty narrow cut, actually, as you can see. But not all oil fractions are so narrow. For example, kerosene, as I told you earlier, starts at about 170 or so and ends up at 270. Uh, so, so basically, this is how you ASTM D86 is, and the way we actually do this. So, this volume percent and temperature, this data we actually represent on a graph. So, on the graph we have, as I told you, temperature on the y-axis and volume percent or weight percent on the x-axis. And this is actually the data. If you plot it, actually forms like a graph here, and it forms like a curve. And right up to this is about 360 degrees centigrade. This is about 360 degrees Celsius. And above that, I need vacuum because at 360 it will crack. The hydrocarbons will crack. So then above 360, I need vacuum. So vacuum is also up to 520, 530, maximum 560 degrees Celsius. And then beyond that, we don't know because we don't have the capability to distill it any further. So what we do is that this dotted line that you see is just an extrapolation from this whole line. So right up to from this, so you can see that it says almost 0% till about something like 48%. We get so 48% recovery is right up to 360 degrees Celsius, and then from 48 to something like 75% recovery is up to 560, and beyond 75, that is the rest of the 25% is the vacuum residue. So this is how actually you represent the distillation data on a graph called distillation curve. And these distillation curves can be anything. It can be D86, it can be D1160, or the other that I talked about. Now, if you look at these laboratory distillations, you have two types, not two, rather three types of distillation that you would have seen. So if I go back here, you would see that you have TVP. Then there are two which are actually analogous to each other, ASTM D86 and D1160. I repeat, there are two which are very similar to each other, D86 and D1160, which is D86. The only difference is that D86 is done at atmospheric pressure, while D1160 is done under vacuum. And the vacuum that you use is 10 millimeter Hg absolute pressure, so 750 millimeter vacuum. And then the other one is by actually using GC. So similarly, so there are three classifications, generally three classifications of lab distillation. One is called fractionating, the other is semi-fractionating or non-fractionating, and the third is simulated. The fractionating is the TBP, the true boiling point, and I'll tell you how we do that. And the semi-fractionating, non-fractionating is D86 or D1160, while the GC is actually the simulated. So that is why the GC we call it as simulated distillation, because we are simulating the distillation curve using GC. Well, those of you who are familiar with gas chromatograph would know very quickly that gas chromatograph works on the principle of molecular size. And the heavier the molecule, the bigger is its size. So that is why we are able to separate out the various fractions by GC, and because as you actually pass the sample through the column in the gas chromatograph, the lighter molecules come out earlier, and then slowly the heavier and heavier molecules will come out. So this is more or less representing the distillation of the sample, and that is why it is called a simulated distillation. So I will actually stop after this slide, and then we'll wait for some questions. So basically, if you're looking at fractionating distillation, that is this particular block here, we are talking about TBP, that is true boiling point. And how you do it is actually standardized and covered in a method called ASTM D2892. What do we do is that essentially it's a batch distillation, which is we don't go beyond 360. Forget about 400. We don't go beyond 360. But actually, so we have a round bottom flask at the bottom, and then you actually have put a long column having 15 trays on the top of it with a pretty heavy reflux. And whatever goes up beyond that and it gets collected in a vessel, as we measure that, okay, in terms of temperature with respect to volume. And so this is how we actually determine TBP distillation. So essentially, it's a round bottom flask. I do not know whether I have a picture. I used to have a picture. Yeah. So this is how you do. So this is the round bottom flask, and this is the distillation. This is the fractionating column we put on the top here. And once the vapors go through this, so basically there's a good internal reflux that gets formed. And these trays are actually shown here with multiple holes here with a down cover. And the vapors, when they go up, they actually get condensed and the liquid falls down. And here actually you have a method by which you can change the reflux. So you can actually control the reflux back. So the vapors which go up, they condense, part of it actually goes back into the column, and part of it is cooled and then collected in this vessel. And this is a graduated vessel from which you can determine at what temperature. So there is a thermocouple or a thermometer which is put here for you to measure temperature versus volume. So this is how we do it in the lab. And this is so there's a good fraction. Just remember 15 theoretical plates and good reflux, etc., etc. Same thing if you want to do it under vacuum, that is covered in ASTM D5236. So this is a kind of a sister method to ASTM 2892. TBP D2892 covers only up to atmospheric pressure, while this can go into vacuum. So the atmospheric residue that comes out of this can be distilled further here, and again, a very large number of theoretical plates with a But here you can go to pretty high vacuum, right up to for zero point 0.5 to 1 millimeter. The same apparatus that I showed you can be actually connected to a vacuum pump. Because it is glass, nothing happens to it. Glass apparatus you cannot operate under pressure, otherwise they'll break. But glass can withstand any amount of vacuum that you can do. The third, of course, is a short part distillation. It is not relevant right now, so I'll not actually talk about that. But remember these two: the ASTM D2892, that is the TBP distillation at atmospheric pressure, and then 5236, which is TBP distillation at under vacuum. Uh, if you want to, so if you actually go to the semi-fractionating or non-fractionating apparatus, that is how the ESTM D86 is. So as compared to the one that I showed you, let me actually show you once more. I do not know where so actually, if you see the separators, I have a round bottom flask with a long column, something like 15 tray with a good reflux, etc. So that actually there is a complete, like in your, if you still make remember your McApthil diagram and the way the fractionating columns operate. So basically, so there is actually a kind of a heat transfer and mass transfer between the light, most volatile component and the least volatile component. So as the hydrocarbons go above across every tray, the more volatile, the less volatile component they actually condense, and in that process it actually vaporizes the more volatile components from the liquid going as the liquid goes down. So that's why you get a good fractionation between the different volatilities and that's why it is used in TBP. Unlike that, in D86, we don't have any of it. We just have a pot, as you can see, a distillation flask. Okay, so this is just a distillation flask which is heated, and you put 100 or 500 or 200 ml of the sample here, and then you start heating it. And when the vapor comes out, the moment you actually see the first temperature, that means the first vapor has come out. So you note that that is the IBP. And this is actually a cooling water bath through which this pipe runs through. You can see this small pipe, which is the vapor coming out. So it goes through this bath, where actually this is a very, very rough, the old primitive way of doing D86. Now the whole thing is completely automated. So you just have to take a sample, put it in the instrument, and switch on the button, and it actually gives you the graph on the computer straight away. Okay, so this is how actually the liquid condenses and gets collected in this measuring cylinder, and you can actually then see like temperature versus percentage volume, and till actually the whole thing gets vaporized. So the moment you actually see the temperature, the first droplet will drop, and then that is IBP, and then the 5%, 10%, 20%, 30%, 40%, like that. So this is ASTM D86. This is actually this picture I pulled out from some old literature to show you, so that you get a feeling as to what exactly it is. And the current instrumentation, what you buy from instrument suppliers, you can't see none of this. Actually, it just comes in a box. You just put the sample and switch on the electricity and stabilize the whole thing, and it actually gives you the data in half an hour. So this is ASTM D86. The same thing actually is D1160. D86 is atmospheric pressure, as you can see, while this is under vacuum. So it has to be a little bit more sophisticated. But unlike what I showed you here, like we had a fractionating column here, there's nothing like that here, right? So it is just a simple round bottom flask with a heating mantle and a thermometer, and then you just get the vapors up. The only thing is that you have a nozzle through which you actually pull vacuum by a vacuum pump, so you can maintain whatever pressure you would like to. And so the vapors They actually go here, and this is the condenser with the cooling water, and some part of it condenses here. Whatever then gets condensed here. Again, you have a vacuum pump here. So this is a vacuum pump. So you can maintain the vacuum, and then the liquid settles down. It comes down, and you can measure with respect to the percentage volume. So this is all actually completely encased, so that you don't have air leakages, etc. But this is transparent, so you can see. You need, of course, a pump to pump out the material out. Otherwise, it will not come from vacuum to atmospheric pressure. So this is what it